Okay, ladies and gentlemen, you are all welcome to my YouTube channel. If this is the first time you are coming to my YouTube channel, please subscribe. So today we are going to look at the chemical equilibrium, which is this PowerPoint is not made by me. It's actually made by the macro health companies. So I just adopted the PowerPoints to make the video. So I did not make the PowerPoint myself. So what is a chemical equilibrium? A chemical equilibrium is a state where there is no observable changes as the time goes on. So in a chemical equilibrium, it means a balance. So life is always trying to maintain balance. So in everything, we need a balance. So, but in this case, we are going to look at the chemical equilibrium, which is in chemistry. So when we said equilibrium is actually a state where there is no observable change as the time goes on. And of course, we have two types of equilibrium. We have static equilibrium and we have dynamic equilibrium. We have static equilibrium and dynamic equilibrium. So in a case of static equilibrium, there is no motion, but the balance is maintained. But in the case of dynamic equilibrium, there is a constant motion, but the balance is also maintained there. So we have these two types of equilibrium. As I said, we have a static equilibrium, and then we have dynamic equilibrium. We have dynamic equilibrium. So in the case of dynamic equilibrium, it means that there's a constant motion. There is a constant motion. But in the case of static equilibrium, there is no motion. It is static, but also the balance is maintained. So that is chemical equilibrium. So we have static equilibrium, that is a state where there is no observable change and there is no motion. But in the case of dynamic equilibrium, there is a constant motion, but there is no any observable change as the time goes on. So, and then the next thing that we are going to look at under this is the chemical equilibrium. So we are talking about chemical equilibrium. So what is chemical equilibrium? A chemical equilibrium is the types of, or is the equilibrium, or the equilibrium is achieved in terms of the chemical equilibrium is when the rate of the forward reaction and the reverse reactions are equal. It means that in this case, when we are talking about chemical equilibrium, in this case, it means that if you have a reaction where you have, like, for example, if you have nitrogen react with hydrogen, it produce, let's say, ammonia, So in this case, we have to balance the equation. So we have to balance it. And how are we going to balance it? So if we now add 2 here, then we have 1 molecule of nitrogen react with 3 molecules of hydrogen to produce 2 molecules of ammonia. So in the case of chemical equilibrium, the chemical equilibrium is achieved when the rates of the forward and the reverse reactions are equal. It means that in this case, that is why in chemical equilibriums, we usually use a double-headed arrow. Meaning that as the concentration of the reactant is decreasing, and then at the same time, the concentration of the product is increasing, and at the same time, so in this case, it means that the rate of the formation of ammonia is equal to the rate of the decomposition of ammonia at the same time. So it means that the rate of the forward reaction, is equal to the rate of the rate of the backward, reaction. So in a chemical equilibrium is a state where or the chemical equilibrium is achieved when the rates of the forward and the backward reactants or reactions are equal. Of course, remember that in normal chemical reactions, the ammonia here, or the nitrogen here plus water plus the hydrogen is our reactant, and of course the ammonia here is our product. So it means that when we say the rate of the forward and the backward reactions are equal, it means that the rate of the formation of the product is equal to the rates of the decomposition of the reactant. So that is one step of achieving a chemical equilibrium. It means that the rate of the reaction is equal to the rates of the sorry, the rate of the forward reaction is equal to the rate of the reverse reaction. It means that as the ammonia products are produced at the same time, then at the same time that the same ammonia is decomposing to produce the reactant. So it means that the rate of the reactants and the products are equal. So that is chemical equilibrium. So a chemical equilibrium is achieved when you use a double-headed arrow that indicates the forward and the backward reactions achieved at the same rate, that is at the same time. So that is why in many cases, in the case of chemical equilibrium, it's not that there is no change. It's not that there is no change. Yes, there is a change, but you cannot actually observe the change because the rate of the reaction are equal both in forward and the backward reaction. So equilibrium is also achieved when the concentration of the reactant or product remain constant. It means that if the concentration of the reactant and the product remain constant, it means that a chemical equilibrium is achieved. It means that if you have two molar concentration of the reactant and let's say 2 molar concentration of the product. So if the concentration of that reactant and the products remain constant, it means that the chemical equilibrium is achieved. But whenever there is any change in the concentration, it means that the chemical equilibrium is not achieved. Let's say the concentration of the reactant is 2 molar and the concentration of the product is 2 molar. But after some time, you now observe that the concentration of the reactant is decreased while the concentration of the product is increased. So if you have that situation, it means that the chemical equilibrium is not achieved. So it means that in the case of chemical equilibrium, both the concentration of the reactant and the product must be equal or must remain constant. And so also at the same time we have a physical equilibrium. So a physical equilibrium is when you have observable change in the physical nature of the reactant molecules. Like for example, this is a water. So if you look at it here, you can clearly see that the water here is liquid. The water is liquid. You can clearly see that the water here is liquid and here it is gas. So it is a physical equilibrium. It means that yes, the rate of the reaction of both forward and the backward reaction remain the same, but the physical states of the reactant and the products have changed. That is in the case of physical equilibrium. And then the next one, we also have chemical equilibrium. So in a chemical equilibrium, look at it. All the reactant and the particles, all the reactant and the products are on the same, are all in the same phases. You have gas and gas. So you see that you have nitrogen, dinitrogen tetraoxide react to produce nitrogen 4 oxide. So if you look at it, the rate of the reactant of both forward and the backward reaction are the same. The rate of both forward and the backward reactions are the same and they are all in the same phases. So this is a chemical equilibrium. So now, at the same time, we have dinitrogen tetraoxide reacts to produce nitrogen 4 oxide, and at the same time, nitrogen 4 oxide reacts to produce dinitrogen tetraoxide at the same time because we have a reversible reaction. So both the forward and the backward reactions are the same. So now if you look at it, we start with nitrogen 4 oxide. So look at it. This is actually, if you can clearly see the rates from this graph, because this is your reactant. And of course, remember, whenever there is a reaction, before the reaction reaches the equilibrium state, it means that the concentration of the reactant must be decreasing, because in this case, nitrogen 4 oxide is our reactant. So that is why the concentration of the nitrogen 4 oxide is decreasing, and then at the same time, then the concentration of dinitrogen tetraoxide, which is the product. So if you look at it clearly here, you see that as the concentration of the reactant is decreasing, then at the same time, the concentration of the product is increasing. So once they actually reach equilibrium state, when they reach equilibrium state, then there will no any observable change in terms of the concentration because they will be moving at the same rate. they will be moving at the same rate. That is a chemical equilibrium. So you see, at the start point or as a starting point, the concentration of the reactant is decreasing while the concentration of the product is increasing. So when they reach equilibrium state, you will see that all of them, if you look at it clearly, they are moving at the same rate and the concentration remain the same. And that is the chemical equilibrium. So now, so you see, this is the equilibrium. So once it reaches this state, it means that it's reached equilibrium because both the concentration and the concentration of the reactant and the products are moving at the same rate. They are moving at the same rates. So now let's say now you are starting with dinitrogen tetraoxide. So it means that you are starting, it means that dinitrogen tetraoxide is decomposing to produce nitrogen 4 oxide. So in this case, actually, the concentration of dinitrogen tetraoxide is decreasing while the concentration of nitrogen 4 oxide is increasing, because at this point we are just considering a backward reaction. So if you are considering a backward reaction, it means that the concentration of the nitrogen tetraoxide will be decomposing. So that it means that at that case, the nitrogen tetraoxide is considered as a reactant, and also at the same time, the concentration of nitrogen 4 oxide will be increasing, because at that stage, because at the backward reaction, nitrogen 4 oxide is our product. So you see, that is why, if you can see clearly, the concentration of dinitrogen tetraoxide is decreasing while the concentration of nitrogen 4 oxide is increasing. So as the time goes on, they will reach a equilibrium state where there are no any observable change. So that is why here we have the equilibrium state, because it reached the equilibrium state. So both the concentration moving at the same rates. So let's say we are starting with nitrogen 4 oxide and nitrogen tetraoxide. So you see, at the same time, the concentration of nitrogen 4 oxides is decreasing while the concentration of nitrogen 4 oxide of dinitrogen tetraoxide is also increasing. So they will reach a state of chemical equilibrium. So that is actually chemical equilibrium, that we should understand that as the reaction goes on, the concentration of the reactant will be decreasing while the concentration of the product will be increasing, and it will reach a state where both the concentration of the reactant and the product will remain equal and they will move at the same rate, and that is what we call chemical equilibrium. So now let's look at this thing. Assuming now this is a reaction, this is a system. So in this system, we have a starting concentration and we also have equilibrium concentration, and we can also have a ratio of concentration at equilibrium. So now, what do you do now? So now, if you can see clearly here, we can see that we have the concentration of, we have initial concentration of nitrogen 4 oxide, and we have initial concentration of the nitrogen tetraoxides. So we also have equilibrium concentration. So this is the equilibrium concentration of nitrogen 4 oxide and the nitrogen tetraoxide. So to get the ratio of the concentration of nitrogen 4 oxide and dinitrogen tetraoxide, then we now take this and divide it by this, then we are going to get this. And of course, if you are going to get the equilibrium concentration or the ratio of the concentration at equilibrium by looking at the real coefficient of each of the reactions, then of course we have nitrogen 4 oxide have a 2 coefficient. So that's why here it is raised to the power of 2. Of course, if you remember from the reaction, we have 2 molecules of nitrogen 4 oxides that react to produce the nitrogen tetraoxide. So that 2 molar, it means that it's a coefficient, it's always come as a power. So here we have the concentration, this bracket. Whenever you see this bracket, it means concentration in chemistry. So we have the concentration of nitrogen 4 oxide, and it's actually power of 2, and then divided by the concentration of the nitrogen tetraoxide. And of course, if you now take this in this equilibrium concentration and you actually spare it and you divide it by 0.44643, then you are going to get this. So this is how to calculate the concentration or the ratio of concentration at equilibrium states. Okay. So the ratio of the equilibrium, or the ratio of concentration of equilibrium, is called equilibrium constant. So equilibrium concentration or equilibrium constant is always measured as a concentration of product divided by the concentration of the reactant. So if you want to get equilibrium constant, we call it equilibrium constant, Kc. So if you want to get the equilibrium constant, which is Kc, you always look at your reaction, and then you now take the concentration of the product. You take the concentration of the product, and then you divide it by the concentration of the reactant. And if there is any coefficient, you power it. If the coefficient is A, then you power it power A, and if the coefficient is B, then you also power it as B. So as we are doing the classes, we are going to look at how we are going to express the equilibrium constant, which is Kc. So that is equilibrium constant. So now, for example, here we still have the nitrogen tetraoxide, which is decomposed to produce nitrogen 4 oxide, so 2 molecules of nitrogen 4 oxide. So to get the Kc, which is the equilibrium constant, we now take the concentration of the product, and of course the coefficient here is 2. So since the coefficient is 2, so that is why we have raised to the power of 2. And then in addition to this, of course, we have the nitrogen tetraoxide, which is actually the coefficient is 1, so that's why we have nothing here. So if you now look at the previous table, if you now take the ratio of the initial concentration of nitrogen 4 oxide and that of the nitrogen tetraoxide, that is how we arrive at this 4.63 times 10 to the power of -5 from the first experiment. Which one is the first experiment? This is actually, we use this, so this is the answer if you check that one. So it means that this is the experiment 1, this is experiment 1, this is experiment 1, this is experiment 2, 3, 4, 5, and this is experiment 5. So in experiment 5, if you now take these concentrations and this, then we are going to arrive at this. So the next thing is this. So after we do it, then we are going to get this 4 times raised to the power of 4.63 times raised to the power of -3. So assuming now this is our reaction, this is our reaction, and of course A molecules react with A plus B molecules to react with B to produce products, C molecule of C plus D molecule of D. So to actually express our equilibrium constant, it means that we are going to take the concentration of the product, and of course this is our product. So therefore C, we have C, and this small letter C is actually the coefficient of the C. So that is why it's put as a power of C, and then we have D, which is also the coefficient is small letter D. And then after that, we have A and the coefficient is small letter A, and we have B and the coefficient is small letter B. That is how we arrive at this equilibrium constant. So this equilibrium constant is actually stated as according to law of mass action. The law of mass action. And what is the law of mass action? The law of mass action, according to the law of mass action, said that the rate of the reaction is directly proportional to the product of the concentration of each of the reactants. So according to the law of mass action, it stated that the rate of the reaction is directly proportional to the product of the concentration of each reactant. So that is how we arrive at this. So if you are now going to look at the rate of the reactions, we can actually clearly see that, okay, now we can now say the rates. We can actually express it by saying rates of the reaction is directly proportional to the concentration of each of the reactant particles. So if you consider the forward reaction, it means that the rate of the reaction is directly proportional. If you consider the forward reaction, it means that the rate of the reaction of this water reaction is directly proportional to the concentration of each of this reactant, which is A and B. So from there, then we were able to achieve that the law of mass action is actually expressed as this Kc, which is called equilibrium constant. So apart from the equilibrium constant, then we now have this, so you can express equilibrium constant in different ways. So you see, this is our reaction. So from this reaction, to write the equilibrium constant of this reaction is simple. We can just say that, okay, can see clearly we take the concentration of the products and we power it with their coefficient and divided by the concentration of the reactant, and we power it with the coefficient of each of the reactant particles. So now, if Kc, if this equilibrium constant is greater than 1, if the equilibrium constant, that is K, is greater than 1, then what happened to the equilibrium state? What will happen to the equilibrium state? So the reaction will lie to the right. It will lie to the right. That is, it means that it will move toward the product formation whenever the equilibrium constant is greater than 1. So it means that the equilibrium will shift or will lie to the right. And then it means that it will favor product formation. It will favor product formation. So it means that whenever you have equilibrium constant, if this equilibrium constant, that is Kc, is greater than 1, it means that the reaction will lie to the right. It means that it will favor the product formation. And what is the product in this reaction? This is the product. So it means that the reaction will move toward the right. That is, form more of the product. And then when okay, and then now, so of course, you see, this is the reactant. So when Kc is greater than 1, it means that it will produce more of the product. So that is why we have bigger product like this. Okay, so now when the equilibrium constant, which is Kc, is less than 1 or is less than 1, it means that the reactions will lie toward to the left. It means that it will favor the reactant formation. So that is why here we have the product. It means that more of the product will decompose to produce the reactant. And in the case of when K1 or when Kc or when equilibrium constant is greater than 1, it means that the reaction will favor the product formation. It will favor the product formation. So that is actually the situation when we have cases. So we also have homogeneous equilibrium. So homogeneous equilibrium is applies to the reaction in which all the reacting species are in the same phases. So you see, these are the reacting species. So what's the reactant and the product? You see that they are all in the same phases. They are all gases. So that is what you call homogeneous equilibrium. So when you see a reaction in the case of homogeneous equilibrium, then you check the reactant particles and the product. So if the reactant and the product are all in the same phases, if they are all liquid, or if they are all gases, or if they are all solid, so it means that they are homogeneous, or they exist in homogeneous equilibrium. So that is why here you see they are all in the same places, which is gases. So now to express the equilibrium constant, so now the Kc is equals to, you now take the concentration of the product to power it by 2, because the coefficient of the product is 2. So then we now divide it by the concentration of the reactant. So now, so if we have homogeneous equilibrium, so we can also have K, apart from Kc, we can have Kp when we have a gaseous reacting particles. So in the case of gaseous reacting particles, we can use Kp. So Kp is just, you say, the partial pressure of the product divided by the partial product, the partial pressure of the reactant. So so this is how to measure Kp. So Kp and Kc. So Kp is applied to only gaseous particles. So you see in these reactions, to measure Kp is simple. To measure Kp, what we are going to do is just to say, okay, so Kp now is going to be, so this is our products. So we are now going to say the partial pressure, then we have NO2, and of course we have the coefficient. The coefficient is 2, so we now put it here as a power. And we now divide it by, so we have the Kp. So for the Kp of the product, then we have P, because of course this is the reactant. So we have N2O04, sorry, O4. And of course, because the coefficient here is 1, so it's just 1 here. So there is no need to even put it. So this is how to get Kp. But we should know that Kp and Kc are not the same. Kc is not equals to Kp. So you see, in most cases, Kc is not equals to Kp. So we have this. So if you look at it, all these, they are all in gaseous, they are all in homogeneous equilibrium. So to measure Kp, so Kp is equal to Kc. So the relationship between Kc and Kp is that, so Kp is equal to Kc times open bracket molar gas constant times temperature raised to the power, close bracket, and raised to the power of delta n. And this delta n means the change in the number of moles. So the change in number of moles, it means that the number of moles of gaseous products minus the number of moles of the reactant. So like, for example, in this case, because the number of moles of gaseous product is 2 and the number of moles of the reactant or the moles of gaseous reactant is 1. So to get the delta n, it means that we are now going to say 2 minus 1. So with reference to this equation, so the number of moles, or the change in the number of moles, we are now going to say the number of moles of product, which is the coefficient of the product. So we are now going to say C plus D. So C and D, small letter C and D, reflect the number of moles of the product. And of course, we have minus, which is minus the number of moles of the reactant, which is small letter A plus small letter B. So now we also have, so under this homogeneous equilibrium, we have this. We have acetic acid, which is ethanoic acid, react with water to produce ethanoate plus hydroxonium ion. So in this case, if you want to actually measure the equilibrium constant, of course, we know that the concentration of water, is always constant. So that is why it's usually neglected. The concentration of water is constant. That is why it is always neglected. So therefore, the Kc now is going to be the concentration of the products divided by the concentration of the reactant. And of course, we neglect the concentration of water because it's as a constant. So that is why we have Kc is always actually expressed as this. So because water is constant, so that's why we neglect it here. So therefore, we have this. So in the general practice not to include units for the chemical equilibrium constant. So now we have some examples. The equilibrium concentration of the reactant or of the reaction, or the nature or the equilibrium concentration of the reaction between carbon monoxide and molecular chlorine to form carbon monoxide chloride at 74 degrees centigrade are 0.012 molar, then chlorine is 0.054 molar, and then COCl2 is 0.14 molar. So we have to calculate the chemical equilibrium, or the equilibrium constant Kc and Kp. So I think this is simple. So this is the reaction. We have carbon monoxide react with chlorine to produce what you call carbon dioxide chlorides. So they are all in gases. It means that they are under homogeneous equilibrium. So now, of course, we are now going to express it. So this is our product, and there is not any coefficient here. So we have this, and of course, the key. So here, the concentration of COCl2 is given as 0.14. So that's why we have it here as 0.014. So we have it as 0.014, which is the concentration of the product, which is given here. And then the next thing is actually the concentration of CO. It's already given, which is 0.012, and we have it here 0.012. And then times the concentration of the chloride, which is 0.054, and of course we also have it here. So after we compute the values, we are going to have 220 as a Kc value. So we now calculate the Kc, and then the next thing is the Kp. So for the Kp, we are now going to use Kc times R times T raised to the power of delta N. So now to do that, we are now going to have, of course, the number of moles of, or the change in the number of moles of the gaseous and that of the product. So the change in the number of moles of the product minus that of the reactant. The product is 1, and of course the product is 2 because we have 1 carbon monoxide here, have 1 molecules of carbon monoxide here, and 1 molecules of chloride here. That is why when we add it, and of course this is our reactant and this is our product. So our product is only 1 mole. So that is why we now say 1 minus 2, and that's why we arrive at minus 1. So now, of course, we have our R value, which is constant. Is constant value is always given. So it's constant, which is 0.0821. And of course, we have the temperature here at 74 degrees centigrade. So we're now going to add it with 273. We get our temperature in Kelvin. So then we now substitute the value by saying Kp is equal to 220 times open bracket 0.0821 times 10 raised to the power of 347 open and close bracket. We have our minus 1. Of course, we have 7.7. So this is another question here. We have the equilibrium constant Kp for the reaction. The equilibrium constant Kp for the reaction. 2 molecules of nitrogen 4 oxides react to produce nitrogen 2 oxide plus oxygen. And of course, the Kp is given as 158 at 1000 Kelvin. So what is the equilibrium free joule? Equilibrium free joule of oxygen if the PnO2 is 0.480 m and PnO is 0.2. So it means that in this case, we are to calculate the partial or equilibrium free joule of oxygen. We have to calculate the equilibrium free joule of oxygen. I think if you can now look at it clearly, it's simple. What we are going to do, we are now going to say, okay, we are now going to say Kp is equal to, of course, the product is, so we are now going to say PnO, and of course, this NO has a coefficient of 2. So we have this then times oxygen, which is PO2, and the power is 1. So we are neglecting that since it is 1. And then the next thing is that of the reactant. So we have NO2 and its power of 2. So the next thing that we are going to do is to make this subject of formula. So how do we make this subject of the formula? By saying Kp, we multiply it is by 1, then we now multiply it times P2 NO2, of course, divided by P2 NO. Then we have PO2. So I think from here you can see that it is simple. We are now going to only substitute the value. The Kp is 158 times we have NO2. So for the NO2 we have 0.4. Then we square it. Then divided by the divided by PnO. So the PnO is also power 2. So we have 0.270. Then we square it. So after we press our calculator, you will now do the all calculation. Then you are going to arrive at your answer. So that is what actually happened. That is what actually happened here. So you see, we can see clearly that at the end, after we now substitute the value, we are going to see, so the PO2 is now being actually changed, or is now changed to the subject of the formula. So after that, we now have 347 atm as the equilibrium free joule of oxygen. So now the next thing is heterogeneous equilibrium. So in heterogeneous equilibrium, it applies to a reaction in which the reactant and the product are in different pieces. Like for example, there is calcium oxide, so it's decomposed to produce, so the calcium triacylcarbonate is now decomposed to produce calcium oxide plus carbon dioxide. So of course we have calcium oxide, we have carbon dioxide, and then we have calcium. So to express the equilibrium constant, we are now going to take the product here, calcium oxide plus carbon dioxide, this, and of course they all have coefficient of 1, so that is why there is no any power. We have this. So because calcium oxide is solid, so they are constant. Calcium tricarbonate is solid, so it's constant, and calcium oxide is also a constant. So therefore, at the end, we have our Kc only by considering CO2. So therefore, the Kc will now be Kc prime times the calcium oxide concentration. So the calcium tricarbonate concentration divided by the Kc. So they are constant. So we are going to neglect that. And of course, for the Kp, it's just the equilibrium pressure of carbon dioxide. So the concentration of solids and pure liquids are not included in the expression of the equilibrium constant. So we should know that this is actually very, very important. It is very, very important. We should know that the concentration of solids and the pure liquid is not included in the expression of equilibrium constant. It's not expressed in the concentration of equilibrium constant. So it's very, very important. We should know this. So whenever you are actually expressing equilibrium constant, you should be very careful first by observing the solids and the liquids. So if they are there, then we need to exclude them from the expression. So now we have this, we have calcium oxide, we have, of course, this is a free reverse reaction. So you see, we have calcium oxide, we have calcium trioxocarbonates, and of course we have calcium oxide, and we have calcium oxide here at the same time, then we have calcium trioxocarbonates. So the partial pressure of oxygen is something as a Kp. So we are only considering the gas that is actually evolving, which is carbon dioxide. But it should be in a closed system. It should be in a closed system. So calcium trioxocarbonate does not depend on the amount of calcium carbonate or calcium oxide. We should know that it doesn't depend on either of the two, either the calcium trioxocarbonate or the calcium oxide. So now following the equilibrium at 293 Kelvin, we have ammonium sulfides break down to produce ammonia plus sulfide gas. So of course, if you can see clearly, the ammonium sulfide is solid and that of ammonia and hydrogen sulfide are all gases. So how are we now going to express the partial pressure of each gas? And of course, the partial pressure of each gas is 0.265 atm, and calculate Kp and Kc. So you see, from this case, we are going to first to start with calculating Kp. So of course, since this one is solid, that is ammonium, hydrogen sulfides, they are solid, so we are now going to include it in the expression. Of course, as the question says, the partial pressure of each gas, because here we have two gases. So you know that the partial pressure of ammonia is 0.26 and that of hydrogen sulfide is 0.65. So it's all the same. So we just take them and multiply them. So we get our Kp. So since we have Kp, then from the relationship, the formula that said Kp is equal to Kc open bracket RT close bracket raised to the power of delta. So we are going to apply this formula. So of course the Kp is non-RT, R is constant, and T is given as 293, and then we have delta N. So we have this, so Kc is equal to Kp. So because in this case, our product is this and this, so they are true, and of course this is solid, so don't consider it. So that's why you consider it as a 0. So we have 2 minus 0, so that's why we have 2 here. And our temperature is 295, is given from the question. Sorry, it's not 93, it's 295. So after we do that, then we are now going to do all the calculation, and at the end we were able to get 1.20 times 10 to the power of minus 4. Of course, here it tends to minus because we make Kc subject of the formula. Yeah, that's why here it tends to minus delta N. So now, assuming now we can have reactions where you can have a multiple reactions, and at the end to get maybe to obtain equilibrium constant. So you see, this is a reaction. We have first reaction where A plus B react to produce C and D, and we have C plus D to react to produce E and F. So the Kc for the first reaction, the Kc for the first reaction is concentration of the product divided by the concentration of the reaction, which is concentration of C and D divided by the concentration of A and B. And that of the Kc of the second reaction is EF divided by C and D. So now you just consider them because you can cancel the reactant and the product. And of course, at the end, this CD and CD of the first reaction will cancel C plus D of that the second reaction, because this is what you call like the reaction mechanism. So reaction mechanisms may involve so many reactions, but at the end you end up having overall reaction. So this is the overall reaction, because here you have A plus B to produce E and F. So at the final, or from the overall reactions, it doesn't need to know what actually happened at the step, because of course at the step of the reaction, C and D are produced, and that C and D at the same time react to produce E and F. So that is the reaction mechanisms. But at the end, it doesn't require, or at the reaction mechanism sometime, we are just only after at the end of the reaction, we are just only after the reactant and the product that is generated. So to get the Kc, then we are now going to have EF divided by the concentration of A and B. So Kc, you can now take it and multiply the Kc of the first reaction, that is the Kc prime and Kc prime prime. So at the end, so if a reaction can be expressed as a sum of two or more reactions, then the equilibrium constant for the overall reaction is given by the product of equilibrium constant of the individual reactions. So now this is another reaction. So in this case, we have the nitrogen tetraoxide breakdown to produce this. Of course, from our previous table, we have this value of Kc. And of course, this is another reaction. And at the same time, we have this. So this is the product and this is the reactant. This is the product. Of course, so if you look at this one and this one, the second one, this one is a reciprocal of this one of the first reaction split. So when the equilibrium of a reversible reaction is written in the opposite direction, then the equilibrium constant becomes the reciprocal of the original equilibrium constant. So you should know this when it is actually considered, when the equation for the reversible reaction is written in the opposite direction. So the equilibrium constant becomes the reciprocal of the original equilibrium constant. That is what happened here. So write the equilibrium constant expression. So the concentration of the reactant species in the condensed phase are expressed in molar. And the gaseous phase, the concentration can be expressed in molar or in atm. So you should know this, there is a unit. So it is expressed in molar. But if they are all in gaseous phases, we express it either in molar or in atmosphere. So the concentration of fuel solid, fuel liquid, and solvent do not appear in the equilibrium constant expression. So we should know this. And then the equilibrium constant is a dimensionless quantity. It doesn't have units. So in quoting a value for the equilibrium constant, you must specify the balanced equation and the temperature. So if reaction can be expressed as a sum of two or more reactions, then the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reaction. So now the next thing that we are going to look at is chemical kinetics and chemical equilibrium. So if we have A react with 2B to produce AB, then we have KF for the forward and we have KR for the reverse. So the rate of the forward reaction, the rate of the forward reaction, because of course remember the rate is always expressed or is directly proportional to the concentration of the reactant particles. So the concentration, so the rate of the forward reaction, we are going to consider A and B because we are considering the concentration of the reactant. So that's why we have Kp We have rate of forward is equal to Kf concentration of A times concentration of B raised to the power of 2. And then for the reverse reaction, we are considering, because in the reverse reaction, our reactant is AB2. So that is what we have. Rate of the reverse is equal to Kr open bracket AB subscript 2 plus the bracket. So therefore, at equilibrium, it means that the rate of the forward and the backward reactions are the same. So that is why we have Kf and Kr. So we now equate the two equations. So after equating them, we are going to have Kf over Kr. Then Kf over Kr is the same thing as Kc, which actually reflects the equilibrium constant of the products. Equilibrium constant by expressing the concentration of the product divided by the concentration of the reactant. So we have what we call the reaction quotient. So the reaction quotient is calculated by substituting the initial concentration of the reactant and product into the equilibrium constant concentration. So if the Kc, which is the reaction quotient, is greater than Kc, then the system proceeds from right to left to the equilibrium, to reach the equilibrium. Yeah. So reaction quotient. So if Qc of the reaction, if Kc is greater than, if Qc is greater than Kc, it means that the reaction would favor right, or would favor from right to the left. It means that it should favor more of the product formation. It means that it should favor more of the product formation. And if Kc is equal to Qc, if Qc is equal to Kc, it means that the system is at equilibrium. It means that no net change. There is no net change. So Qc is greater than Kc, it means that the reaction will favor the product formation. And of course, if Qc is greater than Kc, it means that the reaction will favor the reactant formation. It means that the reaction will favor the reactant formation. So if Qc is greater than Kc, it means that the product or the reaction will favor the reactant formation. So that is why if Qc is less than Kc, the system proceeds from left to the right to equilibrium system. And if Qc is equal to Kc, it means that the reaction is at equilibrium. So now we are now going to calculating equilibrium concentration. First, express the equilibrium concentration of all the species in terms of the initial concentration and a single unknown x, which represent the change in concentration. And then second, write the equilibrium constant expression in terms of the equilibrium constant, knowing that the value of the equilibrium constant solve for x, and then having solved for x, then calculate the equilibrium concentration of all the species. So now, let's have this example. At 1280 degrees centigrade, the equilibrium constant Kc for the reaction, we have bromine react to produce bromide ion is 1.1 times 10 to the power of -3. So if the initial concentration of the bromine is 0.036 molar and bromide ion 0.012 molar, calculate the concentration of this species at equilibrium. So now first, let X be the change in concentration of bromine molecule. So this is the bromine. So the initial concentration of bromine is given as 0.063. And then that of the bromide ion is 0.012. And then the change in concentration is not known. So remember the X, because the bromine molecules is the reactant, so it means that its concentration will be decreasing. So that is why it is represented as -X. And of course, the concentration of the product, because here we have two molecules of bromide, it is going to be positive because lower in the reaction as the concentration of the reactant is decreasing, then the concentration of the product will be increasing. So that is why in terms of the change in the concentration of the reactant is minus X, because we only have one molecule of bromine, one molecule or 1 mole of bromine molecule. And then we have 2 moles of bromide ion. So that is why we have 2X, but it's positive because in a reaction, the concentration of the product is increasing and the bromide is negative because the X is negative because the concentration of the reactant is usually decreasing until the reach equilibrium state. So therefore now the equilibrium M is now going to be the change in the concentration. So we are now going to say the initial concentration minus the change in the concentration. So that is why we have 0.063 minus X, and that of the bromide is now going to be 0.012 plus 2X. So after we have this, then we are now going to have the equilibrium constant. Now we're going to have our equilibrium concentration. So we have bromide. This is our bromide. So the bromide is going to be 0.012 plus 2X. Then we open and close bracket, we square it because we have 2 molecules of bromine. And then that of the product is 0. So that of the reactant, which is the bromine molecule, is now going to be 0.063 minus. And at the end, we have the Kc, which is already given in the questions as 1.1 times 10 to the power of 3, and this is it. So now we have 1.1 times 10 to the power of minus 3 from the questions given, which is our Kc. So after this, then we are now going to solve for X. So at the end, after we now have this, then we are now going to change it into this. So the equations will now change to 4x squared plus 0.04x plus 0.00014 then is equal to 0.000693 minus 0.000x. So it means that how do we get this is by cross multiplication and open this bracket. So that is how we arrive at this. So after we now do this, then the next thing is, of course, to get so you see, after we do that, then we now get this. So we now obtain a quadratic equation. So from this quadratic equation, we can just apply a formula. So then a formula method, x minus b plus o minus b squared minus 4ac equal to 2a. So of course, from quadratic equation, we are going to compare it with our equation of quadratic. So this is our equation of quadratic. And of course, our a value here is 4, still 4. And then our b value is 0.0491. And then our c value, because this is our b, which is the coefficient of x, and it is also here. And then c, which is the constant, is here 0.000747. And after we now have this, then the next thing is to do the substitution in the formula and get the answer. So after we do the substitution, then the answer for x1 is minus 0.0105, and for the x2 is minus 0.00178. So at the end, we are now going to substitute the values obtained from the above for we to get our equilibrium concentration. So at equilibrium, then the bromine is equal to bromide ion is equal to 0.012 times 2x. So after we now substitute the value of x, then we now ending off 0.009 molar or 0.00844 molar when we substitute both for the x1 and the x2. Because this is, let's say this is our x1 and this is our x2. And of course, for the bromine concentration, since we have 2 values of x, then we are going to substitute each of this value here. So at the end, we either have this and this. So then after this, then we are now going to, because we are not going to use negative value, so we are going with this. So this one and this one, we are taking them away. So as a result of that, we are going to use the one that will give us positive. So at the end, at the chemical equilibrium of bromine molecule, we have 0.062 minus x, and it gives us 0.0648. So we are taking that one. So this is how to calculate the equilibrium concentration from the initial concentration. So then the next one is Chatelier principle. Chatelier principle. So Chatelier principle states that if an external stress is applied to a system at equilibrium, then the system in such a way, or the system will adjust in such a way that the stress is partially offset and the system reach in the U equilibrium position. So whenever you have a system that is at equilibrium, and the system is adjusts by maybe a stress or something is now adjusted, then the system, then the way the stress, then when there is something like that, then the system will offset and then it will now reach new equilibrium state. So remember, in everything in life, we wanted to achieve a balance. So if you have an external system that is applied to a system that is already at equilibrium, then the system will adjust in such a way that the stress is partially offset as the stress reaches a new equilibrium position. So if there is anything that actually changes a system that is already in the equilibrium, so the system itself will now adjust, will now change a new equilibrium position so that to maintain the balance. So like, for example, what of now, maybe you have a system that is already in equilibrium and you now change the concentration of the equilibrium. Assuming now this is a reaction where you have nitrogen react with hydrogen to produce ammonia. So assuming now you change the concentration or you add ammonium ion here. So it means that you distort the equilibrium system. So you add the concentration of ammonium. So when you add the concentration of ammonium, it means that the concentration of ammonia, which is the product, is higher than the concentration of the reactant. So what happened at this stage? It means that the equilibrium will shift to the left to offset the stress. So it means that since the equilibrium of the product, which is ammonia, is higher than that of the concentration that is there at the reactant. Remember, equilibrium is reached when the concentration of the reactant and the product are constant. So now you add the concentration of the ammonia, which is the product. So the equilibrium will shift toward the backward direction, that is to the left, so that to offset the stress in order to reach new equilibrium position. So that is look at it. This is the initial concentration. So at this initial concentration, they are all at equilibrium. So now there is now a change. So you now change. So after you now change, let's look at it here. They are all in equilibrium at this stage. But now there is a change by adding or by increasing the concentration of the ammonia. So the equilibrium with the reaction will now shift to the backward. So that is why here, look at it, our reactant is hydrogen and oxygen. So that is why the concentration of nitrogen would increase, and also the concentration of the hydrogen will be increased here. But the concentration of the product, since it is the one that increased, or that is actually increased at the initial stage, then it will start decreasing until they reach another final equilibrium states. So change in concentration continued. So when you now change the concentration, let's say you increase the concentration of product, then it will now shift to the left, that is toward the backward reaction, that is the reactant. And then of course, if you decrease the concentration of the product, then it will now move to the right, so that to produce to the right, so that to produce more of the product, so that to produce more of the products for the equilibrium concentrations to achieve. And then what if you now increase the concentration of the reactant? Then the reaction will now move toward, or will now proceed to the right. That is to produce more of the product. And if you decrease the concentration of the reactant, then the reaction will move to the left, so that at least the concentration of products will be decreased toward the direction of the reactant formation for the equilibrium concentration to achieve. Then still under the Chatelier's principle, what if there is a change in volume and pressure? So the change in volume, increase in pressure also shift the equilibrium to a site where there is a fewest number of moles. Assuming now in the reaction you have, at the reactant you have 2 moles and in the product you have 4 moles. So now if you increase the pressure, then what will happen? Then the reaction will move toward the direction of 2 molecules, because the number of moles of the reactant is 2 molecules. So it moves toward the reactant formation. And then after that, is actually decreased in pressure. So if you decrease the pressure, then it will now move to the site where the number of moles is the most. That is where there is the highest number of moles. Let me just give you examples. In this case, let's say we have nitrogen. Let's say we have nitrogen. Let's say we have nitrogen react with hydrogen to produce ammonia, NH3. So let's say here we have 2, because here is 2. So we have 3 here. So now the number of molecules here in the reactant is 4 mole, while here is just 2 mole. So it means that in the case when you increase the pressure, so the site that has the fewest, or that have the fewest moles, is the product. So it means that if you increase the pressure, the reaction will move toward the product formation. And if you decrease the pressure, then the site with the fewest, or the site with the most number of moles. So it means that by decreasing the pressure, it means that the reaction will move toward this direction, because the number of molecules in the product are higher than that of, the number of molecules in the reactant here is higher than that of the products. So that is this. So now, what if now the next thing, you see, if we can now look at from this reaction, they are all in gases, so the C have only 1 mole. So that is why as you increase the pressure, then it will move toward the C formation. And then if you now decrease it, then it will now, if the pressure is decreased, then it will now move to the site where the number of molecules is high. And then if you now increase the volume, then it will move to the site with the most number of moles. So it means that increase in volume also leads to, or is related to, the increase in the number of moles. So it means that if you increase the volume, then it will move to the direction where the number of molecules, or the number of moles, is high. And then if you decrease it, then it will move to the site where the number of molecules is low. So then, of course, then what happens if there is a change in temperature? So increase in temperature, remember, we can have exothermic and endothermic reaction. So for the exothermic reaction, if there is an increase in temperature, then the key value, that is equilibrium constant, will decrease. And then if there is actually an increase in temperature, so in the case of endothermic reaction, the equilibrium constant would increase. And of course, decrease in temperature increases the exothermic reaction and then decrease the endothermic reaction. So as we now look at this reaction, we have nitrogen trioxide flows 2 molecules of nitrogen, 4 oxides. Of course, by looking at the delta H, since it is negative, it means that the reaction is endothermic. So now, this is a cooler situation, and of course, this is a hot. So next thing is by adding a catalyst. So catalyst does not change K. It doesn't change equilibrium constant, and does not shift the position of the equilibrium system. It doesn't do that. The system will reach equilibrium sooner, but the system will reach the equilibrium sooner. It means that the reactions, the rate of the reaction will increase. So as a result of that, then the equilibrium system will increase very fast, because generally when you are adding catalyst, so the catalyst usually decrease the activation energy so that the reaction can easily occur. So as a result of that, if you add catalyst, it means that both forward and the backward reaction will actually proceed progressively. So therefore the equilibrium position will be attained as fast as possible by decreasing the activation. Because remember, activation energy is the energy barrier that actually occurs, that causes a lot of, or is an energy barrier that must be overcome before the reactions to take place. So generally, the catalyst decreases the activation energy, therefore the reactions will be very fast, the rate of the reaction will increase. So catalyst lower activation energy for both forward and the reverse reactions. Then catalyst does not change the equilibrium constant or shift the equilibrium. So chemistry in action, assuming now you have, I think, ladies and gentlemen, we are going to stop here. And I wish that, okay, if this is the first time you are coming to my YouTube channel, please subscribe. If this is the first time you are coming to my YouTube channel, please subscribe. But please watch this video very well and follow it off. Okay.